Let's begin. So we're very happy to have Alexey Kondratiev from St. Petersburg. Alexey published in such eminent journals as Operations Research and Management Science, and today he will talk about more applied part of his work. Alexey, you have 1 hour, 30 minutes. The floor is yours.
Yes, thank you.
1 hour, 1 hour, sorry. 1 hour, 1 hour.
I'm glad to see you and thank you for inviting me. It is my second time when I present this research. Yesterday I presented it to several agronomists in Rabat. I hope that they will join our project and will contribute to it, because without agronomists it would not be possible to make a good research in this field. So it's a mixture of theory and application, and from a theoretical point of view, the results are marginal to the existing theory, because my main point was to connect theory with a real application. And the title is very pretentious, several words you know. So I call it that power mean is the well-known family of aggregation procedures, is the best method from axiomatic point of view for a particular problem in plant breeding, where you need to select a cultivar or a genotype for growing in the real farming field. And it must combine two not opposite but complementary objectives, which they call yield and stability. So yield, they call it yield, but we know it as just arithmetic mean yield, when you calculate yield as arithmetic mean. And stability is a vague concept, and they have tens of different ways to measure stability. So I will start with can you close your microphone, please? Thank you. I will start with an example of input data that we have in our model. Actually, it is the standard model in aggregation theory, and but agronomists are not very well familiar with it. So in our model, we have candidates. Agronomists call them genotypes or cultivars. I use notation G1, G2, and so on. So in our particular example that I will use, we have 10 genotypes. They are candidates. Each candidate is evaluated by voters. In their problem, voters are called environments. Environments can be a combination of location, year, and management treatment. So but we can think about them as just voters. And in this example, we have 5 voters environments, and each genotype has some yield in each environment. So here numbers mean, for instance, 13.32 means that genotype 1 has 13.32 tons per hectare in environment 1. So here numbers are yield on the area. And numbers in parentheses are just ordinal ranking in each environment. For instance, environment 1 ranks genotype 1 in the first position because genotype 1 has the highest yield in that environment. Genotype 10 is the last ranked and has ordinal rank 10. So I have spent almost 1 year reading articles in agronomy. hundreds of articles. So I will explain something, but I am not agronomist. If I am wrong, so I'm sorry. Genotype. So suppose we have we have an institution ICARDA in Rabat. They breed new genotypes of wheat. And they do it in greenhouse or in glass house or in plastic house. And they make breeding between different existing genotypes to get a new genotype, and then they have maybe hundreds and sometimes thousands of new genotypes. It means that it's genotype. Type of wheat with a specific set of genes. Yeah. Okay. Yeah, it's a good question. So genotype is you can think about cultivars. Okay. So on the right you can see the row where I calculated the arithmetic mean yield. Yeah. Yeah. No, environment is just environment treatment. So environment one could be, for instance, location at specific point near Rabat in the real field, in a specific particular year, under specific management for the amount of fertilizers that you apply. No. What plant breeders do, they just try to create a new cultivar for commercialization. When they create a new cultivar, they will give it to plant producers, to farmers. No. It is not done by farmers. It is done before farmers will grow it in the field. So it is done by a research institution. Why mean is important? So mean is important because mean. Oh no. Yeah. E1. Here I contracted, so usually you don't have E1, E2, E3, E4 because we have 5 waters in our model. In their model, they usually write Rabat, year 2024, 100 kilograms of nitrogen per area. Exactly. Exactly. It's a and management. Yes. So generally, environments are not anonymous. They have marks: year, location, management, and so on. This question is to their field, so they do it. Yes. So actually, when we talk about this specific problem, suppose for a minute that you have already chose the set of target environments. You cannot choose year, of course, because you will grow your cultivar year by year, so you cannot choose it. It will be a random variable to you. I mean, each year will be a particular realization. Yeah. So, but you can fix the set of locations where you will grow your cultivar. So suppose that you have already chosen that I will introduce to the market the best genotype for all locations near Rabat and Casablanca under a specific management. Okay, and then farmers will grow it. So arithmetic mean yield means that it somehow estimates how much yield you will get from the whole area by farmers.
This is very reduced form, right? So you have a lot of genotypes, you have a lot of years. Whenever you try to, with the arithmetic mean, you try to estimate the quality of genotype.
Yes, yes.
Many other regressors that you can introduce. Again, arithmetic mean is basically the estimation whenever you don't have any characteristics of the environments, but you should introduce them in order to estimate, right? You have other controls.
Exactly, exactly.
Arithmetic mean is probably very naive.
No, no. You're asking right questions. They have a lot of different regressors, yes, when they study genotypes. And it is one of the problems in the field. And yield is still the main characteristic that evaluates genotypes eventually. Because when you breed something, you cannot control many characteristics, especially weather. And then only practice will show how good is your genotype. And to understand it, you need to grow it, and then to estimate yield.
But you can control based on the happened year, location and other characteristics. Again, I don't want to push that. I mean, yeah, but it seems like arithmetic mean is very naive way.
It's yes, it's very naive, but they use it. We I I have not thought about it deeper. Sorry. Yeah. Yeah, just like. Yeah. Okay. 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 Yeah. Yes. Yes. As I understand their literature from my yesterday talk with the agronomist, he explained me that the most important characteristics of genotype are the two. One is the yield in kilograms, in tons that you can get. And another one is the variation of that yield. But variation, they measured in different way. So here on the slide, I have only arithmetic mean as the main characteristic, because if you're a farmer, you will grow your grain, and then you will sell it, and the price is per kilogram of your grain. So yield is the main characteristic. But okay. And here is the mathematical model, rather simple. I'll just explain notations that I use. So GI, I denote genotype. It can be cultivar or a cropping system, everything that you evaluate. I suppose that genotypes come from the natural numbers. Environment is a voter in our model. It can be location year pair, or location year management treatment, something like that. I also suppose that genotype or environments are numbered by natural numbers. The main characteristic and the only characteristic in our model, it is the basic and the most simplistic problem in the field. so the quality of genotype I in environment J is measured only by yield. So Yij is the non-negative yield of genotype I in environment J. And a profile consists of a finite number of genotypes, finite set of genotypes G capital, some finite set of environments E capital, and the matrix is indexed by these sets, as on the previous slide. And we will consider two types of domain for profiles, from where profiles come. In the fixed domain, we will fix the set of genotypes G capital and the set of environments E capital. We suppose that they are finite, fixed, and contain at least two elements. So all profiles in the first domain will come from different number inside the matrix. Yield? So mathematically, yield for us is just a non-negative real number. For agronomists, yield is the amount of grain in kilograms per hectare. Yeah. Another type of domain, the second type I consider, is variable domain. I will post several restrictions on it. So I have a parameter, M capital J is the maximum number of genotypes in a profile that I can elaborate. It is not less than 3, but we can put this parameter as plus infinity. So it means that, so the only restriction is that the number of genotypes is not more than the parameter, M capital J. If M capital J equals plus infinity, it means that in our domain, profiles can have any number of genotypes. So our notation, so I denote Rij as the rank of genotype I in environment J according to the ordering of yields. So each environment ranks genotypes and give them ranks. But the problem, so so in real field, of course, all these ranks will be just point numbers because the probability that two genotypes will have the same yield is 0. But mathematically, we should suppose that they can be the same, which will happen with probability 0. But in our model, we should suppose. And I denote, so if several genotypes have the same yield and in the same environment, for instance, and they occupy ranks from K to K plus L minus 1, so I denote rank of the genotypes as a set. Usually, a typical way to elaborate with it is just instead of working with set, we just take point estimate of this rank. For instance, if several genotypes occupy ranking positions 3, 4, 5, then the point estimate will be 3 plus 5 divided by 2, so it's 4, the middle. Alexey, you are again asking a good question. So sometimes researchers, they can collect a complete matrix. But typically, if the number of genotypes are hundreds of locations, maybe tens, and environments more than tens, of course, they have some missed values. And the second part of our paper considers exactly the case of not complete profiles. Yes, yes. Especially in official trials that happen every year. And in each year, so official means that, so it's official in a country. And in some countries like Germany, you cannot just introduce your genotype for commercialization to the market. This genotype must show good yield in such an official trial. But the input profile will be not complete because each year you evaluate only subset of genotypes. Some genotypes are benchmarks. They are grown in the field for many years, and they will be in evaluation for several maybe years, maybe tens of years, but they will be too old. So usually it is a diagonal matrix, typical in official trials. So in reality, yes, yes. So complete profiles happen not in official trials, but in trials for research purposes. And it is one of the reasons why we will need, and actual agronomists use, some sort of normalization of data. They do not use yield per se, and they normalize it somehow. It will be on the next slides. And normalization is motivated by the fact that the profile is not complete. So a ranking rule for each profile P on the set of genotypes G and environments E gives us a ranking, a complete and transitive order of genotypes from the capital set G, so genotypes from the profile. So here in our model we have that ranking can be non-strict. So it's complete, but it can be not strict. Some genotypes can be ranked equally. The outcome of the ranking rule, as usual, I call the aggregate ranking, and it may contain the type. Exactly. And that applied everywhere. Netflix ranking, movies, everywhere. Exactly. Yes, yes. But this work, I focused specifically on this particular application, not even thinking about other applications. So we have already mentioned that because we have missed data, and another fact is that we have different environments in terms that in one environment you have irrigation, and the genotypes give you high yield. Another environment can have not irrigation, can be not irrigated, and because of drought, your genotypes can give you a low yield. So it is not fair, to consider the yield numbers without normalization. It is a discussion, but they actually use some sort of normalization. So and most of them are presented on this slide, and we compare different types of normalization in our model. So we will not have regressions in my yeah. So what are you talking about is relevant, and I am not special in statistics, and the main approach that they have used so far is statistical approach. And if you will be interested in this problem, I think that you could read with me. Maybe I will show you the main articles, and we will see what they do wrong from the point of view of economists, because they are not familiar with approaches that you use, I think. So they do regressions, but I cannot say more if they do the same as you mean. Because they have not read economics articles. They haven't read economics approach. You will see why. So I will apply not statistical approach. I will try to apply the aggregation theory, which has not been applied so far in the field. So I haven't found an article which applies anything except statistical approaches. So we of course, so okay, let we have a profile. We consider the following ways. Without normalization, the typical way is just we divide our yield by the maximum yield collected in that environment. So then you will have, in each row, you will have one if the genotype gave you the maximum yield in that environment, and all other numbers one or lower, but not less than 0. Also, you can subtract from your yield, subtract the maximum yield in that environment. Then the best genotype in that environment will have 0 in the matrix, and all other genotypes will have 0 or less. A fine normalization, we just subtract a minimum yield in that environment and divide by the range between maximum yielding genotype and minimum yielding genotype in that environment. So after this normalization, all numbers in our matrix will be in between 0 and 1 will be if and only if the genotype gave you the maximum yield in that environment across all genotypes that were evaluated. And the genotype will have 0 quantity in the matrix if that genotype was the worst genotype in that environment. And we also consider ordinal normalization when our input data are only ranks of the genotypes in that environment. Formally, we define 0 by 0 equal 1. And so we say that a ranking rule uses normalization X if the outcome is the same for all profiles that coincide after normalization X. In simple words, it means that such a ranking rule only uses information after normalization. So, and the information before normalization is lost. So, clear? Outcome is the aggregate ranking of genotypes. I should not have used synonyms. So here on the slide, I will start. So I will talk about axiomatic approach, not statistical approach. And for all of us, the axioms are familiar. So as economists, we all know them, but unfortunately, and it was the most surprising thing for me, is that in plant breeding, they have no clue about axiomatic approach, they have no clue about axioms, desirable properties, and also they don't have theorems, for instance. So for us as mathematicians, the problem looks like we have the set of ranking rules, or maybe if I formalize it in a different way, we had the set of selection rules. And then we want to pick up one rule or several rules from this set, or using some motivation, and we motivate it by desirable properties, which we call axioms. So, but the first part is that we had the set of mathematical objects, in our case ranking rules, from which we want to select one of them and use it in reality. And usually in theorems, when we state even a theorem in statistics, fundamental theorem, we start with the set of objects. So we formalize everything, and we have the set of objects for which we prove something. For instance, we prove that this statistical method is the most efficient in the class of such methods. So we formalize the class of methods for which we prove that this method is the most efficient. But for me, it's surprising that in their literature, but their literature is purely practical. It's agronomy, crop science. They drag some methods from statistics, but they do not take from statistics theorems. So, and also, so it's more general problem that they not only have not been using axiomatic approach. They even have not been using so far the formal mathematical approach that we are familiar with. And here are some basic properties that, so yesterday was Monday, yes. Yesterday I talked with Tadesse Vulitav from the plant breeding lab. And he accepted that all the axioms that I have chosen for this presentation are desirable for the problem. Because some of the axioms that are not maybe are discussive, I just left them in the working paper, but not in the slides. So we say that the ranking rule is weakly Pareto efficient if for each profile where genotype I was better than genotype K in every environment, was better or equal. Yeah? Then in the aggregate ranking, genotype I will be ranked equally or higher than genotype K. So weak Pareto efficiency confirms the weak comparison. So a ranking rule is Pareto efficient if it is weakly Pareto efficient, and for each profile where genotype I gave us strictly higher yield than genotype K in each environment, then also in the aggregate ranking, genotype I will be ranked higher than genotype K. In the plant breeding literature, it was motivated actually by Miad et al. Many years ago, but successfully have been lost. We say that the ranking rule is monotonic if whenever you have a profile and you have a genotype and its yield in some environment, and if you increase that yield without changing anything else, then the ranking of that genotype will be the same or higher relative to the ranking of other genotypes. So it's a usual axiom for us. It is very closely connected with Pareto efficiency, in fact, mathematically. And what I asked my student 1 year ago is to verify tens of different methods that the agronomists use for ranking genotypes and verify for them the Pareto efficiency and monotonicity properties. She have done it successfully, and of course, intuitively, I knew it. She showed that most of them violate Pareto efficiency. And this was the most surprising thing for me, because they can use Pareto inefficient rules, which means that sometimes they will select inefficient genotypes. But in fact, they are not familiar with the fact. Even if they have one article actually sometimes cited, maybe even hundreds of times cited, but they just still ignore the fact that their rules are not Pareto efficient. Okay, so maybe I will skip this part because I have only 20 minutes. You can believe me that rules they use are not Pareto efficient. It's just computational check. Yes. On the last slide, I will have 4 examples of rules that are weakly Pareto efficient. But I don't want to go deeper in that bad rules. So here are examples. So she verified for our profile. So the profile is unique for all rules. The different statistics that they use, and this example shows that what they do is not Pareto efficient. So we introduced further several axioms, and our results will be based on the fundamental theorem of Roberts. So the next important axiom is strict independence of irrelevant alternatives. It means that a removal of a genotype from a profile leaves the aggregate ranking of the other genotypes the same. We all know this axiom, and actually it is also known to the plant breeding community. It was published, so it was mentioned in several old articles. But also they decided, as a community, they decided to ignore this fact and to ignore that this axiom is important, just because almost all statistical procedures will violate this axiom. And a weaker axiom is just independence of irrelevant alternatives. We do not change the set of genotypes, but if the yield of a genotype in a profile changes without changing anything else, then the relative order of the other genotypes is the same. So this is an arrow-like axiom. And another very important axiom is a ranking rule satisfies what I call multiplication invariance if multiplying all quantities in the profile by a common positive number leaves the aggregate ranking unchanged. Usually it is motivated that we can measure the yield not in tons per hectare, but in kilograms per square meter, for instance. And this axiom actually is satisfied. So I did not verify it formally, but my intuition says that as I see formulas, most of the rules that they use will satisfy multiplication invariance. Another axiom that we define is separability. It is due to the model of Roberts. We say that environment J is indifferent if all genotypes in this environment give the same yield. So this environment is not discriminative enough. Yesterday, Tadesse said me that they even will not use such a kind of environment because this environment will not give them additional information. And separability says that if we change the yield in an indifferent environment so that this environment is still indifferent, then the aggregate ranking of genotypes does not change. So it's separability. Weak dictator is an environment such that if in this environment the yield of genotype I was higher than the yield of genotype K, then the same will be reflected in the aggregate ranking. If all yields are different, then weak dictator becomes the dictator. And we claim just that no environment is a weak dictator. It's also very natural axiom, because otherwise it would mean that the only our target environment is just this one environment. And I added to the model one axiom on my own, but actually it is very similar to the axiom of reversal introduced by Fortemps and Pirlot in a similar model. So I found their article, and then realized that I can define in my model a very similar axiom, which I called reversibility. The agronomists also said that this axiom is desirable in their setting. It means that, so suppose you have a profile and you have a genotype and his yield in some environment. And this yield was, for instance, 10 tons per hectare. And then if I will approach this yield to 0 without changing anything else, then the ranking of that genotypes will approach to be the last in the aggregate ranking. So at some moment, this genotype will be the last ranked. No, not in one. any profile with positive numbers, with positive. Yes. Hmm? It will be the last ranked. It's not to the last, to the zero yield. Yes, yes. And what Tadesse said, so the agronomist I talked to yesterday, and I hope we will work together to publish it. He said that it is natural to their problem because actually, if a genotype gives a zero yield in some year at some location, they will it will be a red flag for them. They will move it out and they will not introduce it to the market. They want a genotype that will give at least some yield every year in every target location. It is very important for them. No farmer will grow a cultivar which can give him zero yield. Uh, in each particular profile. It works only for each fixed profile. Then you just change one number in it. Yeah, yeah. This axiom claims that all numbers in the input profile. Yeah. Because you cannot, you can, because you cannot decrease them simultaneously. Sorry, could you repeat? Yeah, okay. Okay, okay. No, no. All the axioms in the model are independent, logically independent. All the axioms I have introduced are logically independent. All these axioms I have introduced are logically independent. So, of course, of course. Yeah, yeah. 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 Yes. This axiom is actually very restrictive, and it is desirable only for this application. So here are a little bit notations that we need. So, yeah. No. Yeah. Yeah. To satisfy IAA, we need some cardinal aggregation functions. So here I introduced not ranking rules, but I need a little bit notations. So as we see, each genotype is characterized by the vector of numbers yield in each environment. So for a profile P and a genotype, suppose we have xi, so xj. Xj here is its yield in environment J. So it's the vector. And xj is the performance of the genotype in environment J. So the aggregate performance of the genotype can be measured by a function which the theory calls cardinal aggregation function, which takes the vector of yields and returns you just one real number. And then you can compare the performance of two genotypes, just comparing those cardinal outputs. So we say that a cardinal aggregation function weakly represents a ranking rule if whenever the aggregate performance of genotype which yield vector was x is better than the cardinal performance of the genotype which vector of yields was y, then x must be ranked above y. So arithmetic mean weakly determines in this sense some ranking rule, but this definition does not say anything when f at x equals f at y. So it can rank genotypes equally or one above another. It says only when the cardinal aggregation function is sure that one genotype is better than another one. So then taking any cardinal aggregation function, we can generate different ranking rules, at least on almost all, for almost all profiles. So suppose we have a finite set of environments E capital, and WJE is the weight of environment G when we have this fixed set of environments. The total weight is equal to 1, all weights are non-negative. And so the weighted power mean is expressed by the following formula, which I know that you are familiar with. It has a parameter alpha, is the power, and actually alpha can depend on the set of environments I have, formally. In practice, maybe they will use alpha global, so alpha will not depend on E. But formally, I should say that alpha can depend, at least can depend on the set of environments. And then, so power mean with this parameter alpha of the vector x is just is the sum over all environments, and weight of that environments we multiply to the performance of the genotype in that environment, power alpha. And then taking 1 divided by alpha doesn't mean anything for our problem because it doesn't change the ranking. So for the ranking, the main part is here. If you take alpha equal 1, you will have just arithmetic mean. If we take alpha 0, the formula will approach the geometric mean when we just multiply all performances, power weight of the environment. So the power mean family contains arithmetic mean with alpha equal 1, geometric mean with alpha equal 0, the harmonic mean with alpha equal -1. And when the parameter goes to minus infinity, we will have the minimum aggregation function. And so here on the slide I collected all the theorems, but using the way that will be clear for agronomists. So I do not write words theorems, but each row in the table is a theorem. And each theorem actually is an application of the basic result of Roberts, which is in the first row. So here we consider the model with complete profiles and fixed sets of environments and at least 3 genotypes. We suppose that yield is positive and apply the axiom of independence, Pareto efficiency, and several other axioms. So for instance, with multiplication environment and separability, we have that the only way to rank genotypes is to use minimum, maximum, or the weighted power mean with some parameter alpha. It's the yeah. And you rescale it. Yeah. Yes. So the agronomist said me that all axioms are desirable in their setting. So if we apply all axioms, it means that we should use the minimum function or the weighted power mean with the parameter not more than 0. So the geometric mean or other power means that are closer to the minimum function. And if you like those axioms, you should use those rules. Actually, it is a very simple implication from the fundamental result of Roberts. So for us, the theory is just well known. And it will be very hard to explain it to the agronomists because they're familiar with statistics and they think in statistics point of view. And also, they do not think about axioms. They always think about particular profiles with fixed yield numbers in it. They cannot think about potential yields that can change in profile. They cannot think about the family of all rules from which you select. So it might be very tortuous, so hard. Yeah. Yes, yes. And it is hard for them to think about Pareto efficiency because they say that if I see a concrete example of a profile, I will immediately see that this genotype is better than the other genotype, and that I will see that I should not select this genotype, which is Pareto inefficient. I will do it. So Tadesse said me yesterday. But he cannot think in terms of ranking rules. He will still use a ranking rule that is Pareto inefficient, but in the same time, he said that he respects Pareto efficiency because for each real profile, he will respect it. And they still cannot see the incompatibility between this way of thinking. It means that actually they do not follow the rules that they think they follow. So they do ad hoc changes to the rule that they use. Weights? So axiomatic approach cannot say us how to choose the parameters. So we still have a parameter alpha of power and weights of the environments. And I think that we should use statistical approach to tune the exact values of that parameters. Because axiomatic approach will never answer to this question. So the next thing that we have studied is that we need normalization for several reasons. And then also we have a normalization here, this row. And if I apply multiplication normalization, so I get some positive result that I can use weighted geometric mean, and weights should be more than 0. If I apply translation normalization, where I subtract the maximum yield, then I should use, I can use only arithmetic mean. But it is, for us, for this problem, the arithmetic mean is just an impossibility result, because they want some balance and between arithmetic mean and stability, and this means that closer to minimum. And I cannot use affine or ordinal normalization because of the famous results of Sen and Arrow that we can use only dictator rules, but not for this problem. The geometric mean, yes. This two? Second and third? No, because I have yes, yes, yes. So if there is no any y in this table, it doesn't mean that the rule does not satisfy it. It means that if I claim that I have IIA, Pareto efficiency, separability, and multiplication normalization, then it should be geometric mean, and it also satisfies reversibility and multiplication invariance. So maybe so it is my first presentation. So all y means that they are applied in the axiomatic characterization theorem. So maybe I should have write down that y star, which means that they are used in axiomatic characterization, and y means that they are satisfied but not used in axiomatic characterization. Yeah. No, normalization.
So you have this normalization.
Yeah.
But you still have other properties.
Sorry, normalization is a property of what?
Normalization. So normalization actually is an axiom also, because axiom is everything that narrows down the set of rules in our domain.
Sorry, I just confused.
Multiplication normalization.
You have the axioms on the left, the 4 axioms.
Yeah.
Let's fix the first 3. It means the set of axioms,
This.
dictator rules that satisfy these axioms are that written on the right, correct?
Yes, exactly. So this implication means that.
Oh, it's implication from left.
Yes. Sorry. Sorry.
Yes.
Yeah. Sorry. So. Sorry. Because actually, so yeah, I understand your confusion, because it is not complete characterization. In the theory, it is called almost so it is almost characterizations, because you read it as a ranking rule satisfies IA, Pareto efficiency, multiplication invariance, separability, reversibility. Then it must be weakly represented by minimum or weighted power mean with such parameters. And the reverse, the reverse statement is that every function that is represented by the minimum or weighted power mean with that parameters will satisfy that axioms. Those axioms. Sorry. For the next time, I will know how to explain it. The contradiction, because I have not explained you what does it mean represented by. I only had a definition of weakly represented by. So that.
So your question, now I understand better, because I was thinking that in the third line, this method doesn't satisfy
Yeah.
You can characterize them by these two axioms, and moreover, they satisfy the other.
Yeah. The geometric mean is the only rule that satisfies all the axioms we have considered so far. So I will put all y's here and use y star for axiomatic characterization. It will be easier for the audience. I agree. Okay. Yeah, it's fine. It's great that you are asking. Also, I will be happy, and maybe the agronomists will be happy if some of us also will join to make some contribution to their field, because they are not familiar with.
Money, we are ready. You tell them. We need just money.
I hope to visit them again this week. Again, so. So here is similar theorems that are proved in my paper, but proved means, but so if I will send it to an operations research journal, they will say they are proved. It's almost straightforward implication from the theorem of Roberts. So the main contribution is practical, so to make a bridge between theory and practice. And here I consider just a variable set of environments and genotypes. So the profiles come from the world where the set of genotypes, the set of environments can change. And that is why I can apply strong independence of irrelevant alternatives, also separability, Pareto efficiency, and several other axioms. And also, the main result is that what the maximum set. So the main result here is that if we need to use multiplication normalization, then the only rule is the weighted geometric mean that we have so far. So the axiomatic approach gives a rather limited amount of rules, but at least it is not empty. At least we should be happy that we have geometric mean which satisfies all the axioms and is compatible with the multiplication normalization. Yes, exactly. So it appeared in many other.
Usually, when you do egalitarianism, gives you the mean and match product.
Yeah.
And welfarism.
Yes, exactly.
Some of utility social. Somehow.
Clear connection with what we have studied so far. And also, we proved that these properties on top. No, not these properties. Even translation normalization is incompatible with reversibility and monotonicity. Affine normalization and ordinal normalization are not compatible with reversibility, which means that if we want the largest set of desirable properties, we need to use multiplication normalization. Also, I had several results for incomplete profiles, but I will not talk about it today. But mostly the implication is the same, that we have more impossibility results when we have incomplete profiles, but when we have, so at least something, that geometric mean will be the best. So in their literature, actually, the geometric mean was proposed by Riza Mohammadi from Iran and Ahmed Amri from Rabat, but he retired last year. At least Odessa said that he retired last year, so that's why I cannot connect with him, with Ahmed Amri. They proposed it in their literature, so they used the geometric mean in their literature, but do not know that it is the best rule from the axiomatic point of view. Also, they proposed several rules that are weakly Pareto efficient, but they are not so good with respect to other properties. Sometimes these two do not satisfy Pareto efficiency, reversibility, any independence axiom. And the best rule, which is closer to geometric mean, is the power mean with the parameter alpha equal 2, because when we use translation normalization, all the numbers become negative. We take power 2 of those numbers and sum up them, but that procedure will violate strict independence or independence of relevant alternatives and reversibility. So the best rules are from the power family that we have discussed. And the main conclusion is that, so we want to select what? We want to select how to normalize data and which formulas to use. And the axiomatic approach says us that we should use multiplication normalization, which means that divide by the maximum yield in that environment, and weighted geometric mean for the parameter alpha 0. Geometric mean is defined by the parameter alpha equals 0, and it will give us the best axiomatic properties. So if you want that properties, you should use it. But if you want to change the balance, so geometric mean is a concrete balance between arithmetic mean and minimum yield. If you want to change the balance, axiomatic approach says that you will need to sacrifice some desirable properties. If you're ready to sacrifice the independence of irrelevant alternatives, then you can use the parameter alpha less than 0, so to be closer to the minimum yield. If you use alpha more than 0, that you will additionally sacrifice the reversibility property. So I think that, so in practice, which alpha to choose is the most important question, and it will depend on the country. Because, for instance, in exporting countries like Russia, which export a lot of wheat, alpha can be close to 1. Almost arithmetic yield is important, because Russia will always cover our all needs. But alpha should be less than 1, but maybe we don't know which exact value of alpha to choose. It should be done in the further research, and we cannot use here an axiomatic approach. We should use here some optimization techniques or statistical techniques. It is inevitable. And for instance, for growers from countries like Morocco, where what you grow is actually what you will eat, stability is more important than for farmers in Russia. Then you should use alpha maybe 0, or maybe even closer to, so -1, or I mean closer to minimum. But how to choose, we don't know. But the answer is that alpha depends on the country, on many other characteristics of farmers and their preferences.